Welcome to the Journey Shake Cam. Today's warm-up, dot diagrams. You just gotta love those dot diagrams. Well, do the best you can and be careful. There may be something you need to pay special attention to in there, and we'll go over them in a moment. In number 1, we are drawing dot diagrams of these formulas. And this is a polyatomic ion. And chlorine is in the middle. And chlorine is S2P5, therefore it has 7 electrons in its outer energy level. 1, 2, 3, 4, 5, 6, 7. The -1 means 1 electron was gained in this. And I mark it as a negative to show that I've taken care of that one. And oxygen has 6 S2P4. And I just put them on the sides. And then every element has an octet. And I circle my octets. Kind of missed that one a little bit, didn't I? But you know what that should be. And then I draw the line diagram. And when I draw the line diagram, I see that these oxygens are bent 2 with a 105-degree angle, and I need brackets to show that -1 charge. And then, so I gave the shape, the angle, and told you the structure, and we also need to know the polarity. Well, these lone pairs of electrons are very negative, and therefore this molecule is polar. And also, whenever it's charged, it is also polar. So for 2 reasons, this polyatomic ion is polar. In the second case, selenium is in the center of this molecule. Selenium is S2P4. 1, 2, 3, 4, and I'm going to put 1 electron on each side so that it can bond to the fluorine. Because fluorine is S2P5, which is 7 electrons, it wants 8, and therefore the 8th one will be shared with the selenium. And again, this is bent 2. I draw my circles around the octets and my circles around these fluorines, and I see that I have the selenium with the 2 lone pairs, and now I do not need brackets because this is not charged. The brackets are required when it is a charged particle. And this is polar because of these 2 lone pairs. We see that the electrons are pulled, the negative is pulled where the lone pairs are, and we show that this is slightly negative on this side and slightly positive on the other side of the molecule. And therefore it's polar. And the angle would be 105 degrees. And there you have it. And there you have it. I wanted to show you something about this bent 2 molecule. And because I wrote these lone pairs on one side, I wanted to show you this dog toy, which is very fun. And the general shape is a tetrahedron, but 2 of the lone pairs are on one side, and it doesn't matter which side I put it on because they still will be together on a side. So whether it's above or below, we must recall that this is a 2-dimensional representation of a 3-dimensional item. And therefore, These, I write them on the same side. If you were to draw it with one on top and one on bottom, that would be fine in a two-dimensional representation. But you need to be aware that in a three-dimensional, the actual molecule, the lone pairs are on one side or the other. And I'll be right back. In 1C, we see that we have calcium chloride, and calcium is a metal and chlorine is a nonmetal. And we should notice that right away. We have a metal with a nonmetal. That is a salt, and salts do not have molecular shapes, and I was wondering if you were paying attention to that. And therefore, it is a crystal lattice. It has a crystalline structure like our table salt. It's a crystal, and therefore it does not have a molecular shape. It has a crystal lattice. And they have cubic lattices. And there is no shape as far as molecular shapes go. However, it is polar because it is composed of a positive calcium and a negative chlorine. And therefore it is polar, but there is no shape. So you need to pay particularly close attention to that and catch those if you see them sneaking in. Now in D, we have arsenic with 3 bromines. And whether this is C and D or 3 and 4, it doesn't really matter. And I'm going to write my arsenic has an S2P3, and therefore there are 5 outer electrons. 1, 2, 3, 4, 5. And bromine has 7, and each one will join with the one available from the arsenic to get its octet. And that way, every element has an octet. We have an octet around the arsenic and each of the bromines. Now, when I see the line diagram, I see arsenic with its lone pair and the bromines. And it is trigonal pyramidal with an angle of 107 degrees. And it has this angle because this lone pair is very, very large electron area. And the shared pairs are very small because they're shared between 2 nuclei. Therefore, they have to stay in between there, which limits the space that they can take up. Now, because of this lone pair, it is very negative on this side of the molecule and relatively more positive on the other side. And sometimes we see an arrow which will be pointing towards the negative side. Either one of these descriptions shows the polarity. And therefore this side would be slightly positive. So it is a polar molecule. Now, in number 2, it asks for what is the difference between shared pairs and unshared pairs of electrons. Well, a shared pair, as we said, goes between 2 atoms, between the nuclei of 2 atoms. And an unshared pair is between the atom and nothing else. No other atom is attached there. And so the electron cloud for an unshared pair or a lone pair is very much larger than a shared pair or a bond pair. Shared pair is another way of saying bond pair. And unshared pairs of electrons are lone pairs. So it's some terminology that we need to become familiar with. Now it's pretty exciting. We're going to learn about the expanded octet. And I'll be right back. Now we are completing the chart with those compounds that have greater than an octet. And this occurs when we get to the 3rd energy level, because in the 3rd energy level we pick up the d orbital and there's room for those extra electrons. The 1st energy level only has an s orbital, and the 2nd energy level only has an s and a p. Therefore, it's only in the 3rd energy level that we can have an expanded octet. And we need to write this down because even though you were given a chart it is very helpful to write the chart as well, because we are taking a written assessment and we need to write it down. And by writing, it's a same brain function, and you'll do better if you do write these notes down. Instead of just watching, it's helpful. Now, the first one that we're going to talk about is AsBr5. And in some respects, these are easier to figure out because arsenic has 5 valence electrons and bromine has 7 valence electrons. And therefore, each one of the bromines wants one of the arsenic's electrons. And when I draw this, I see that each one will be shared with a bromine. And therefore, we have 10 electrons around the arsenic. And each one of the bromines will have an octet. And the outer electrons, or the outer atoms, will have an octet. And only the central atom has greater than an octet. And in this case, we have 10 electrons around the arsenic. And when we look at this, if we were drawing the line structure, we would just have 5 lines coming out. And when we look at it on a two-dimensional, it's very difficult to see the actual shape of this molecule. And therefore, I have a wonderful model for you. I can't use balloons because balloons get very confusing with 5 balloons and it just doesn't work out as well. And these models are very, very helpful. Now, you can see that this is both a trigonal planar and linear. So we have actually 2 angles that are going on here. And what I'm going to do is all of the ones that have 5, whether it's 5 bond pairs and no lone pairs, or 2 bond pairs and 3 lone pairs, we call that the steric number, is based on the 5, is what we have here. And this name is kind of fun, and the name is trigonal bipyramidal. And we had 5 bond pairs and no lone pairs. And we had 120 and a 90-degree angle. Now, when you get the assessment for this information, I will give you the chart. I will give you the shape and the bond pairs and the lone pairs and the angle, but I will not give you an example. And when it says using the table above, you will know that all of those molecules will have an expanded octet. So that's a heads up for you. Now, the second one that we're going to do is SF4. SF4. Now, sulfur has 6 valence electrons. 1, 2, 3, 4, 5, 6, because I know that each one of the fluorines wants one of those valence electrons. And therefore, I have this. And I'm pretty fast at drawing these X's. And it will take you some practice to get skilled with this, and you have some for homework. And that's always helpful to practice. And therefore, again, I have 2, 4, 6, 8, 10 valence or 10 electrons around my central atom, and my outer ones follow the octet. The outer ones will want to follow the octet. And when I look at this in the line structure, it would be like this. And when I look at it in the model, I see that it looks like a seesaw. And sometimes I call it a sawhorse, even though it's not exactly like a sawhorse. But sometimes it's called a sawhorse or seesaw. So we have seesaw or sawhorse, and it has 4 bond pairs and 1 lone pair. Now, this angle is 177 and 104. And again, you don't have to memorize these because I will give you the chart on the assessment. Now on this one here, this trigonal bipyramidal, when we look at it, we see that it is going to be a non-polar shape because it is going to have the trigonal planar, which is a non-polar shape, and a linear. And they're equally pulling in all directions, and therefore there is no positive or negative side. However, on the seesaw, when we have this one lone pair, it's very negative on that side, and that would make it polar. And then we have another one, and that one is fun. It's ICl3. And iodine has 7 valence electrons, and 3 of them will be used for the chlorines. And therefore, I am going to have 2 lone pairs and 3 bond pairs. And you're going to know what this shape is called. What do you think? It looks like a T. We call it T-shaped. It is T-shaped. And we had 3 bond pairs and 2 lone pairs. And this angle is 88 degrees. Now, we have one more that has a total of 5, steric number. And that would be XeCl2. XeCl2. Well, xenon, even though it doesn't like to react, it can be put in a position where it will react. Now, xenon has 8 valence electrons, and 2 of them will be used for the chlorines. And therefore, we have 3 lone pairs. Two, 4, 6, 8, 10 valence electrons around the central atom. And let's see what this looks like. I bet you know what this one is. We call this one linear. It is the second type of linear that we've gotten. We had one linear that was following the octet, and now we have another linear that is not following the octet. And the reason why is because these lone pairs are in a trigonal planar arrangement, and they're pulling equally in all directions, and therefore this molecule is non-polar. So we have linear, we have 2 bond pairs and 3 lone pairs, and a 180 degree, and it looks like this. And that would be the linear shape. Now we have 3 more to go, and they're going to have 6 potential bond pairs. And I'll be right back. The next molecule that we're going to do is SF6. Now, sulfur has 6 valence electrons, and each one of those will be bonded with the fluorine. We have 6, 1, 2, 3, 4, 5, 6. This gets a little bit complicated here, and each one of the fluorines will bond with that one electron. And you can see that the outer atoms all follow the octet, and fluorine does not have a d orbital, so it could not have more than that. And we have a total of 12 electrons here. And this molecule, we would draw it like this. But again, that does not give us a good 3-dimensional representation. And I do have another model to show you that we do have this representation. Whoop, I lost a little straw. Now, in this representation, if we imagine that there's a side on each one of these, notice that we have a square in the middle. And so if we look at this and we have a side on each one, we would have 4 sides and 4 sides, which would give us 8 sides, and we call this an octahedral. Octahedral. We have 6 bond pairs and no lone pairs. And we see that we have 90-degree angles all over the place. 90 degrees. The next one that we're going to discuss is ICl5. ICl5. Now we know that iodine has 7 valence electrons, of which 5 of them will be used for the chlorines, and that will leave me 1 lone pair. And it will look like this. One, two, three, four, 5. So I have 2, 4, 6, 8, 10, 12 again around my central atom. And this shape is a lot easier to understand when I look at my model. And you can see that here I have a square, and then I have the bottom of a pyramid, and therefore we call it square pyramidal. Square pyramidal. We have 5 bond pairs and 1 lone pair, and again we have a 90-degree angle. And finally, we have one more shape to go, and this one would be XeF4. Xenon has 8 valence electrons, of which 4 of them will be used for the fluorines. That leaves me with 2 lone pairs, and it will look like this. We have 4 bond pairs and 2 lone pairs and 90-degree angles. And when we look at this, you can see that now we have this that is in a plane. We have a square in a plane, and we call it square planar. Now, in this case, the lone pairs are on the top and on the bottom, and therefore they do cancel each other out, and this would be a non-polar shape. The square pyramidal, this is a single lone pair, and therefore it is polar, and square planar is non-polar. And those are the shapes that do not follow the octet, that have an expanded octet. Now, this evening, I believe you will have both types of shapes to draw, and it tells you specifically which ones you can expect. Well, you do the best you can. I know you're going to have some fun with this. It's a little bit different than all the math that we've been doing. It's kind of creative. I like that, don't you? Well, I can't wait to see you tomorrow. Bye.